Okay, so there it goes. Right, so here's where we're starting today. This is a new subject. We're going to talk about directional derivatives, something called directional derivatives, and then we're going to study them in relation to the gradient. It turns out there's strong connections between directional derivatives and the gradient, which we've seen before. I'm going to introduce this in kind of a weird way. Roughly speaking, the big punchline of this page of notes is going to be that pretty much what we're doing is generalizing the idea of a partial derivative. Oh, sorry, question.
This isn't on the test, correct?
Correct. Let me just to clarify, a good question. So we are here Friday, September 23rd. And you can see today's material, what I'm going to eventually fill in there, that's in the yellow section. Yellow means fair game for the second midterm exam. So yeah, you're quite right. Today's material is not fair game for the exam. Just while we're here, I'll point out that this is now filled and finalized. These green, the section numbers in the green colored cells are the fair game material for the midterm. Okay, right, cool. Okay, yeah, so partial derivatives. Now y'all know partial derivatives. Roughly what's about to happen is I'm going to generalize the idea of a partial derivative just with the idea that we'd look in different directions. Instead of looking directly along an axis, we might look off axis in some other direction. Okay, the way I'm going to do that, I'm not going to prove my results. I'm going to argue by analogy and hope for believability, because the actual deriving, the actual calculation is really not that important. So the big idea to me is how what we're about to introduce as directional derivatives are morally equivalent. It's the same idea, just that way instead of that way. What's the big difference is basically the case I'm going to make. Okay, so here we go. Partial derivatives. What we know about partial derivatives: they're the slope of a graph. They're a factor that you multiply by, in the sense that, if you have an input change, you multiply by the partial derivative to get the output change. That was one of our other interpretations of a partial derivative. And some things we haven't spent a lot of time talking about, but that you can confirm for yourselves by easy calculations, is that another interpretation of a partial derivative is as this expression. The idea here is that if I'm at a certain point, and if I want to talk about what happens as I move in the, I can do it here, in the xi direction. Well, moving in the xi direction, I can actually manufacture that. I can make that happen. Here it is. There's a parametric line that is moving in the xi direction, because look at the velocity vector there. It's a unit vector in the xi direction. Right? So what this on the inside of f here, what we have is literally a parametric line that's describing exactly I'm at the point A moving with velocity ei. Or said differently, I'm at the point A and I'm moving at unit speed in the xi direction. That's exactly what's on the inside here. And that noted, we're computing df dt. How fast is the function changing while you're at a given point and moving in the direction of a certain variable? Well, that's what a partial derivative is. So, in some sense, it's just the way you talk through this expression is a perfect description of what partial derivatives are. So I think it's pretty believable as well. But if you don't like it, you're not sure you believe it, you're a skeptic, right? You can just compute this directly. This is a chain rule problem, right? Because f is a function of all this stuff on the inside. This stuff on the inside is a function of t. Right? And so apply the chain rule, you'll get exactly this. Nice little exercise. And then also, you can compute partial derivatives with this formula. And again, you can view this in different ways. You can view this as, I think the easiest way to see this is as a special case of the chain rule. Okay, I tell you what, even easier, I suppose, is just multiply out the dot product. Either way is fine. Okay, so we have these several interpretations of partial derivatives. Here's an important distinction I want to make, though. The partial derivative we defined, first cat out of the bag, very first definition we gave was in terms of variables. We're going to hold certain variables constant. We're going to let the other variable be a variable, and then we're going to take the derivative with respect to that variable. It's all talking about variables. Notice, nothing that I have on the page here is talking about variables. We're talking about a slope as I move in the direction of a certain vector. Unit vector, EI. It's a factor that you multiply input change to get output change, assuming you are moving in the direction of a certain vector. Again, unit vector, EI. This one down here, specifically it's the vector EI, describing our velocity. And then over here it is the vector EI that we're dotting with the gradient. Okay, so all written in terms of vectors. So there's nothing on the page here now about variables. If this is all about vectors, I mean, yeah, partial derivatives have certain points of view about variables as well. That's fine. Let's not talk about those. This stuff that we've got on the page has nothing to do with variables. This is just about vectors. And if you get right down to it, these standard basis vectors, not that special, really. I mean, they have certain nice features with respect to variables, right? Coordinates specifically. But as vectors, they're unit vectors that point in certain directions. And I could talk about unit vectors pointing in other directions, right? So the fact that that I can compute, let me erase that. The fact that I can compute this slope, I can compute this slope, aka this factor, with this expression, or alternatively with that expression. The fact that these things are all connected to each other, forget about partial derivatives, the fact that these are all connected to each other in relation to a certain vector, well, you'd think that all these things would still be connected to each other in regards to, well, just in other directions. And it is absolutely true. All of these things that I have highlighted in green all still relate, no matter which unit vector you're using to describe your direction. So we can't use the word partial derivative, of course, because that's already taken. The big idea, generalizing for any other, looking in general directions, is the term directional derivative. And again, it's just a rip-off of partial derivative. You're doing all the same stuff. We're talking about being at a certain point, moving with a certain velocity, and you want to know how the function's changing. Computing with a dot product with the gradient should give us the slope of the graph, should give us that multiplicative factor, all with respect to looking in the direction described by this unit vector. V now, not a standard basis vector, still a unit vector, but just describing another direction. So, I think this is pretty believable. I mean, if you've got a graph of some function, and the claim is that the slope of the graph can be computed by some vector formula, why would that formula only work sometimes and not in other? You'd think it should work in any direction, not just coordinate directions. So anyway, these are all true statements. And again, I'm not going to prove them. I'm not going to do the algebra. Not that bad. If you want to give it a try, totally do it. But I like to emphasize the analogy, and that this is really just the same thing as partial derivatives, just in different directions, and so we have different formulas. Okay. All right. How are we doing? Pausing for questions. Everybody willing to buy that? Okay. Alrighty. Let's draw some pictures here real quick. So slope of the graph, right? So we've seen this for partial derivatives, but let's emphasize now for any unit vector describing a direction. So here's my unit vector V. That defines a direct. Let's see if I can do better than that. It defines a direction like that. And if I look at the cross section, having art problems. If you look at the cross section to the graph in that direction, here's that cross section curve. right? And then if you ask, well, what's the slope of the tangent line? There's the tangent line, and the slope of that tangent line is the directional derivative. This thing called directional derivative. Is that cool? I mean, just like with partial derivative, it's just that it's not a axis direction, so now we call it directional derivative. Okay. Let's talk about the other one here, this business about being a multiplicative factor. So it's what you multiply by input change to get output change. Keep in mind, input change and output change could take a couple of different forms. We can talk about changing by a certain distance in whatever direction we're talking about. In other words, like a discrete jump from I was here, now I'm there. Or we can talk about instantaneous rates of change, which has certain nice perks of not having to worry about the approximation, the limits built in to that, so it's kind of convenient in that sense. But anyway, input changes multiplied by this factor to get output changes. Well, if your input changes are these, and your corresponding output changes are these, how should we write this factor that we multiply by the input changes to get the output changes? And I think it's a pretty easy pitch that this notation here makes loads of sense. What do you multiply by ds to get df? How about df ds? Right, seems pretty reasonable. And I would read this as rate of change of the function with respect to distance. Right? Not to be confused with rate of change of the function with respect to time. Right? These are different things. Okay. So let me elaborate on the difference there between df dt and df ds. So let's suppose that we are hiking along some trail. Right, and at a particular moment, I'm at a certain point, I'm moving in a certain direction, right? And let's suppose the function that we're interested in is altitude. So this f here is altitude. So here's a couple of things I might reasonably want to talk about. I might be interested in, my athletic accomplishment of how many feet of altitude per minute am I gaining here? Am I doing a good climb? I don't even know what a good number would be on that, but seems like 20 or 30 feet of elevation in a minute would be a respectable pace. I don't know. I haven't measured it in a long time. But anyway, let's just say 20 feet per minute might be a nice target. Well, am I doing that? Well, I want to be able to, take all of my information and do a computation and find df dt. How many feet of elevation am I gaining per unit time? Right? So this is a measurement of me and what I'm doing as I'm hiking up that hill. Right? Is everybody cool? On the other hand, df ds, totally different thing. This says how much elevation gain, not per unit time, but how much elevation gain is there per unit distance traveled along the trail in whatever direction you're going. And if you think about it, how much elevation gain, how much up per distance, per unit horizontal, that's just telling you the slope of the trail. How steep is the trail? That's it. It's got nothing to do with you, right, or me. So if I'm hiking along the trail is described by df ds. Features of the trail. How steep is the trail? df ds is intrinsic to the trail, right, to the function, the altitude function on that trail. df dt is about me and my personal experience as I hike on that trail. Does everybody see the difference? Yeah. Okay, so directional derivative computes df ds. And again, I think that's a pretty nice notation for it. Okay. Alrighty. So let's do some examples. So here's a function, and I want to know, the question asks here, what's the slope of the graph? Okay, well, here's the thing. Slope of the graph. I mean, there you go, right? Slope of the graph is one of our first interpretations of the directional derivative. And so the question asks to compute the slope of the graph. Fine, we're going to compute the directional derivative. Yep. Oh, you know what I'm now realizing? I think I didn't comment on the notation here. This is just notation, but this is the notation we use to represent directional derivatives. The unit vector describing the direction in which you're going is just a little subscript. That's all it is. Okay. All right. Okay, so yeah, directional derivative we're going to compute because it's asked for the slope of a graph. Directional derivative. Another formula from the previous page. Now that we realize we want a directional derivative, there you go. It's dot product with the gradient. No problem. One little tricky bit I haven't quite gotten to yet, but is everybody with me so far? Okay. All right, here's the tricky bit. Easy to oops on this. This business about directional derivatives, directional derivative, this notation fitting with these formulas and these interpretations requires that we have a unit vector as our v. It's got to be a unit vector. Now, again, I didn't derive the proofs of these facts, right? So I can't point to the algebraic reason why. But from an analogy standpoint, keep in mind partial derivatives, right? The idea of a partial derivative is that you're going along an axis, and we describe that with standard basis vectors, which are unit vectors. So the analog of the standard basis vector being a unit vector, the analog of that, but pointing in a different direction, still a unit vector. So you should kind of expect that it ought to have to be a unit vector for all of the analogies to come through. Again, I'm not going to show you the algebraic proof. It's not really necessary. Y'all will believe this? Does that seem plausible? Okay. So, it's got to be a unit vector. And here's the problem. We were not given a unit vector. We were given this conspicuously non-unit vector. We want to talk about the direction that non-unit vector is pointing. And keep in mind, in order to describe a direction, I need a unit vector. So what is the direction? What is the unit vector pointing in the direction of a non-unit vector? Standard formula from ancient history, either what was that week 1 of this class, or probably somewhere in Math 218. You just take the non-unit vector and divide it by its own magnitude, and that gives you then a unit vector. And that is what we use for our directional derivative. That then is what we dot with the gradient and the computation of that directional derivative to give me slope. And now it's all algebra from here. Is that okay? Everybody happy? Okay. So heads up about that. If you're going to use all of these properties, you have to have a unit vector. All right. Now, just real quick, let me throw just a little bit of attention to the rest of this. I've got to compute the gradient. Okay, well, the gradient consists of a bunch of partial derivatives. I need the x partial and then the y partial of that function, and those are easy partial derivatives. Don't forget then you also have to evaluate at the point that you're at, right? So this is all evaluated at the point A, and so you're going to have to plug in x equals 3 and y equals 1 to evaluate this, this general gradient to the specific gradient that I actually need at that point. Okay, and then arithmetic. Okay. Here's another little landmine that I want to point out for y'all, so you don't step on it. This phrasing will trip up some students. Let me draw a picture of exactly what this means, and then I'm going to show you what the misunderstanding can be sometimes. So, and I need space for this. So let's see, page. There we go. Okay, so what this means, we are, let's see, at the point 3, 1, And then we've got this vector 3, 4 defining the direction that I go from the point 3, 1. All right, drawing the picture. Here's XY plane. Let's see, the point 3, 1 is about, let's say, there. That's my A. And then let's see, we got this vector V, 3, 4, which would be something like that. And keeping in mind, we want to talk about the direction of that vector, and the direction, of course, we represent with unit vectors, and that's scaled appropriately. Magnitude 1. There's that direction vector. Okay, so this is the right interpretation of what's that question that's written that we've already kind of done stuff with. Here's the misinterpretation. Notice it says here that this is the vector 3, 4. Vectors do not have locations. Very important. Vectors do not have locations. They have directions. They have magnitudes. They don't have locations. When we say the direction of the vector, what we mean is, this being a vector, it has a direction and a magnitude. We want just the direction. Ignore the magnitude. Okay, so that's what we mean here. Some students, though, mistakenly interpret 3, 4 as a point. Not what it says, right? But if you interpret 3, 4 as a point, that point is about here. And you could imagine if you're interpreting that as the point 3, 4, direction of kind of sounds like you're saying toward. Kind of sounds like you're saying toward that point 3, 4. In which case, the student would misinterpret that they should go that way, the unit vector for which would be, I think I'm out of colors. Well, there we go, use black. Be like that. So, of course, that's the wrong direction, because we shouldn't be heading toward the point 3, 4. The question isn't at all about the point 3, 4. Does everybody see the difference? Everybody see why this is wrong and this is right? So it's all about careful, proper interpretation of the language as written. You got to be real careful with this kind of thing. It can mess you up. Okay. Yeah, okay, good deal. Here's another example. And so, we've got a temperature function here. This is temperature as a function of position. So maybe there's a hot spot somewhere. Think of it as a kind of like a campfire or something. And for example, if you plug in x, y, z, all equaling 0, you get 85, right? Nice toasty 85. But then as x, y, and z move away from the origin, this numerator gets more and more, or exponent gets more and more negative, and asymptotically this term goes away, and it's kind of a crisp 60 elsewhere, right? So I like to think of it as kind of like a campfire situation. Okay, so reasonable question you might ask. Suppose you are at this point, and for whatever reason, you're moving in, let's see here, this direction, the direction of that vector. How fast is the temperature changing? Right? Pretty reasonable question. Maybe you're cold. You're hoping, I hope I'm getting warmer. Or maybe vice versa. Right? But how fast the temperature is changing as you move in that direction, reasonable thing to want to know. Everybody on board? Okay. All righty. Well, notice the question explicitly asks for rate of change with respect to distance, aka directional derivative, computed as usual, the usual formula. Again, you have to be careful. You need a unit vector, not just whatever vector you're given. This vector here, in order to give me the corresponding unit vector, I've got to take that vector and divide it by its own magnitude, as you see I have on the right there. So don't forget to make your vector a unit vector. Again, you have to if you want to use the term directional derivative and all the goodies that come along with it. you have to got to make that a unit vector. Now there's a little bit of ugliness in finding the gradient vector. Now this is annoying, but it's tedious. If you got to take this and take the x partial and the y partial and the z partial, and all together there's that gradient vector. And then of course you got to plug in the point. You got to plug in this in for x, y, and z, right? And all together then at the given point, the gradient is that. There you go. And then arithmetic answer. Everybody okay? All right. Very pluggy chuggy. If you interpret things, again, you got to be careful with the interpretations. Okay. Awkward note that has to get made. Outside of Math 219, some people will have a different definition of directional derivative and will remove the unit vector requirement. But wait a minute, I've already made a pretty emphatic point that you can't do that. Right? So what is up with that? How can they get away with just ignoring the unit vector requirement? Let me come back up here. Here's our page where we have all these various properties. Right? And again, you have to have a unit vector as we're doing things in this course. Here's the thing. Even without a unit vector requirement, it remains that this thing here is always equal to that thing there. For appropriately, you need the function to be differentiable. So it remains, even independent of having a unit vector, this is what I'm going to call always true. Now, if you lose that unit vector requirement, then these two things that are equal are not the slope. They are not a multiplicative factor. So that goes out the window. But you still have that these two things are the same. You still have, in other words, that look, if you're at a certain point, and if you're moving with a certain velocity, it doesn't have to be a unit vector, any velocity, and you want to know how fast the function's changing? Yeah, no problem. Compute it as gradient dot whatever that velocity vector is. Doesn't have to be a unit vector. That's still pretty neat. It is very commonly the case that we are at a certain point, moving with a certain velocity, and wanting to know what that does to the function. So this is a useful pairing. This pair alone is a useful concept. And again, some people like to call that a directional derivative. So I want you all to be aware that that's out there, right? But I emphasize that we've got to make a clear, unambiguous choice for Math 219. In Math 219, we're going to go with the unit vector requirement because that's what our textbook does. Right? The textbook requires this vector be a unit vector. And the goodies that come along with that are that the directional derivative, namely that expression, namely this expression, is a slope and it's a multiplicative factor, and we get all the goodies that come along with it. Okay, I just need y'all to be aware that, again, some people make the other choice. And I'm not even making fun of them. Let's see here, yeah. Again, because how fast the function is changing is naturally of interest and is computed with that expression. Okay. And now, so again, I got to emphasize, in this course, we require unit vector. Outside of this course, clarify with whoever you're talking to. So some people use the word directional derivative more generally, and that's fine. And they will not announce themselves as such when you're talking to them. They'll just say directional derivative and assume that you know what the sense in which they intend that. So when you hear the term directional derivative outside of this class, your ears should perk up and think, uh-oh, which school of thought does this person subscribe to? Right? Because it could be either. For the record, I'm one of the other guys. outside of Math 219, I really prefer, my own personal preference is to lose the unit vector requirement. So in fact, the way I do it in my book is I define directional derivative to be these expressions, and then if you in addition add the unit vector requirement, thus in addition giving you these other two interpretations, that I call a unit directional derivative, which I think makes sense. I don't know, I find that satisfying. But anyway, that's not Math 219. In Math 219, unit vectors only. Okay, I've spent enough time on this. Okay. All right. Okay, so let's talk about how to make directional derivatives as big as possible. We're going to assume we have a nice multivariable function, nice in the sense of being differentiable. We are going to be sitting at this point A, and the question is, from that point A, notice that there's a lot of different directions from which I could move. I could go that way, I could go this way, I could go that way. There's infinitely many, there's a whole circle, if you will, of different directions that I could hypothetically move from this point A, right? Of all of those different options, which ways that I could start moving? Which one makes the directional derivative, color choices, which one makes the directional derivative here as big as possible? Yeah. So that is a pretty reasonable question. I mean, just for relatability reasons, let's suppose this is where I am in the middle of the woods. And maybe I want to know which direction should I walk to make my temperature increase the fastest. Maybe I'm cold. Right? I want the temperature to increase the fastest. So I want to walk in the direction where df/ds is as big as possible. Now, how fast I walk in that direction, that's my problem. Right? As fast as I can. That's a given. Of course I'm going to move as fast as I can. But which direction, I want to decide on the basis of which one's going to maximize my directional derivative. Does that seem like a reasonable choice? Okay. Right. So this is a natural, reasonable question. I do want to point out one thing about the question before I get to the answer, and that is this thing that we want to maximize. The directional derivative, keep in mind I can interpret directional derivative as being df/ds. It's how fast is the function increasing with respect to distance? What's the rate of increase of the function in per unit distance, intrinsic to the function itself? With that in mind, if I am looking for whatever the direction is, what is the direction that makes the rate of increase the fastest? I want the fastest rate of increase. I think it's pretty reasonable to call that direction the direction of fastest increase. Yeah? Kind of borderline too on the nose, but that's exactly what we're looking for, the direction in which the function's increasing the fastest. Does everybody see that? Now, here's the thing. You might interpret directional derivative differently. You might interpret directional derivative as slope of the graph. Now, that's a totally different interpretation. Equally valid, totally different interpretation. And with this interpretation in mind, I want to maximize the slope of the graph. Okay, so that means I want to find which direction should I go so that the slope is as high as possible, and if the slope is as high as possible, that means I want to go in the direction that's as steep as possible as I climb, aka ascend the graph. And so they say, with this interpretation in mind, that the direction is the direction of steepest ascent. So both of these terms are fine, perfectly reasonable descriptions of what we're looking for. Again, I haven't told you how to answer this question yet, right? But the answer that we're looking for reasonably could be called direction of fastest increase, direction of steepest descent. Okay. Now, I have a personal preference between these two. It's not a big deal. I'm not going to, make a big thing out of this. But I prefer to call it direction of fastest increase. The reason why is because this does not depend on the perspective that you're taking. If you are thinking about, if this function represents, let's say, temperature again, right? You're not looking at a graph of temperature, you're just experiencing the temperature. Direction of fastest increase very naturally applies as, well, I'm looking for the direction in which temperature is increasing the fastest. So, makes sense, right? In that context, though, again, if you're thinking about F as representing altitude, if you're thinking about it as representing altitude, sorry, I'm talking myself out of it. If you're thinking of the function as representing temperature, still with temperature, what would steepest ascent mean? The function is temperature. I'm walking around on flat ground, right? Perfectly flat ground, and I'm trying to keep track of how the temperature is changing as I walk around on flat ground. In that scenario, what do you mean by steep? Right? It just doesn't make any sense. This point of view, this term steepest ascent only really makes sense if you're looking at the graph, because this slope specifically is slope of the graph. So you're just not always looking at a graph. So I feel like this this terminology here, direction of steepest ascent, is a little bit narrow and presumptuous. What if I'm not looking at a graph? I'm very often not looking at a graph. Sometimes I can't even look at a graph. This always makes sense. Okay, so that's my case. That's why I like this one better. Now, full disclosure, honestly, this is the more common term. So you're going to hear people say direction of steepest ascent. I encourage you to, when you hear that, to think direction of fastest increase. Okay. All right, how to find it. Keep in mind this thing that we want to compute, the directional derivative. That's what we want to maximize. Don't forget, directional derivatives are computed with a dot product. Dot products are computed like so. If you think about it, our unit vectors here all have magnitude equal to 1, so that factor can get thrown away. So what we really want to maximize then is we want to maximize, we want to maximize that product right there. And I observe that the gradient is defined by your location. Gradient is a function of position. It's not a function of which direction are you thinking about going. It's a function of where are you. Right? And since we haven't yet decided which direction we're going, we're at the point A no matter which of these directions we're thinking about. So this gradient, magnitude of the gradient, is a constant. Though really, if you get right down to it, the thing that I need to maximize, if I can maximize cosine theta, we're win. And maximizing cosine theta is easy. You maximize cosine theta when theta is equal to 0. That means that the angle between, the angle between the gradient vector and the optimal direction, the direction that I should be going, that angle in there, that angle needs to be 0. That'll make cosine theta as big as it can be. That'll make the directional derivative as big as it can be. Is that cool? Okay. So I need that angle to be 0, which means my picture is bad. The picture as I have it drawn here, I had to draw it like this because I needed to be able to draw the angle. Right? So you can't draw an angle of 0, which is a hard thing to draw. Anyway, seeing now that angle should be 0, what I realized then is that the actual picture should be this. Right? The direction that I should go should be same direction as the gradient vector itself. So gradient divided by its own magnitude. The direction that the gradient points is the answer to the question. Everybody good? Yep.
How does that account for the sign of the gradient?
How does that account for what now?
The sign of the gradient.
The sign of the... Well, so keep in mind what we're computing. We're computing directional derivative, which is a dot product. and the dot product is computed by this formula. So, I mean, that's just what we have. Maybe I'm not understanding your question.
It's like the vector that lines up with the gradient vector.
Yeah.
But what if the gradient vector is negative?
Well, gradients are never positive or negative. Or, excuse me, vectors in general are never really positive or negative. They just have various coordinates, right? But importantly, in the way we're interpreting vectors here is that they have direction and magnitude. And magnitudes are intrinsically a positive thing. If the gradient was, I mean, if you might want to say it, in this direction, but negative, you might interpret that as just being in the other direction. And if it's in the other direction, then that's the direction that the gradient points. Does that make sense?
Mm-hmm.
Yeah. Cool. Yes.
So does this mean the gradient always points in the direction of steepest?
Yep. That's right. The gradient always points in the direction of fastest increase. That's absolutely right. Yep. So yeah, neat fact. Okay, so again, the big idea is I wanted to make this as big as possible. I know how to do that now, and well, with that in mind, this is how I make this as big as possible. How big is it being as big as possible? What is that maximum directional derivative? How would I compute that maximum directional derivative? Well, I compute it with the usual formula, dot product with the gradient. There's the optimal direction that we've already decided we're going to go. And then notice we have gradient dot itself, which is magnitude squared. And that cancels with the denominator. And therefore this maximum directional derivative is this. It's the magnitude of the gradient. So it's weird, but again, the gradient is the answer to the question, mysteriously. What's the optimal direction? The direction of the gradient vector. How steep is it in that direction? What's the rate of change of the function in that direction? The magnitude of the gradient. So direction of the gradient, magnitude of the gradient. In both cases, the gradient is the answer, which is wild. So I like to phrase this sort of turning it around. Rather than thinking of this as two questions, both of the answers to which involve the gradient, I rather think of it as this is really an interpretation of the gradient. We previously wrote the gradient as an algebraic thing. It's a vector whose coordinates are various partial derivatives. It was a bookkeeping creation, right? It was a tool for notational convenience. That's it. It was a very algebraic thing. Now we have a thoroughly geometric point of view on the gradient. The direction and the magnitude. That's the geometric sort of aspects of the gradient vector. Direction and magnitude. And I'm going to describe these geometric aspects as, well, the direction is the direction of fastest increase, and the magnitude is that maximum directional derivative. Okie dokie. So, let's see here, an example. So, suppose you have a hill. The hill is in the shape of the graph of this function. Keep in mind graph. Graph means that, z is a function of x and y. So that's our hill, and I am sitting at the point 1, 3. Okay, well, kind of. I'm actually sitting up here on the hill. 1, 3, you could argue, is buried underneath the hill. Right? I'm not buried underneath the hill. Not yet. Right? So, here's the thing, this is kind of an awkwardness. It's kind of inconvenient to talk about the actual point on the graph. The point on the graph, recall, graphs are weird. Graphs have x and y input coordinates, but then they also have z output coordinates. It's a very strange thing. These numbers 1, 3, for example, though, by comparison, 1 and 3, those are the input values. So it's easier to talk about location by describing the x and y coordinates and saying, well, yeah, I'm on the hill at 1,3 means, yeah, I'm on the hill. 1 and 3 are my x and y coordinates, and I'm on the hill. So my z coordinate compute accordingly. So it's a little bit of a sloppiness, a little bit of a slight abuse, but these 2 points we very commonly conflate the point under the point on the graph with the point on the graph. So heads up, just to be aware. By the way, there's nothing unusual about this. If you think about it, if you were to describe your location to somebody, and you were to say, oh yeah, I'm at latitude such and such, longitude such and such, they're going to go ahead and assume that you are on the surface of the earth, right? They're not going to, so you're at sea level, but Duke University is 300 feet above, so you're buried 300 feet. No, of course not. Right? They're going to assume you're on the graph of the altitude function. Okay. All right. So anyway, at this point, we want to know, apparently, which way is uphill. So what's the direction of steepest ascent? Well, it's the gradient vector. You can compute the gradient, plug in the point in question. Keep in mind that, we're at this point, 1,3. So x is 1, y is 3. Right? And so altogether, what direction is that pointing? Well, that's pointing, it's the unit vector pointing in the direction of -2, -2, and that's what I'm going to call southwest, in the sense that the y-axis is typically thought of as pointing north, right? And the x-axis is typically thought of as pointing east, right? And in that sense, this is southwest. Okay. Everybody happy? All right. How steep is it there? How steep, namely, what is the slope of the graph? Namely, what is the directional derivative? Well, how steep is it is the magnitude of the gradient. So the slope is 2 root 2. Okay. All right. We have a minute and a half left. I don't think we're going to get anything done in a minute and a half. Let me say one super quick last thing, though. I'm going to draw the line right here. We have been talking up to now about largely about graphs, right? And the interpretations of directional derivatives and gradient, and what's the relationship between directional derivative and gradient in the context of mostly graphs. So next time, next time's the exam, right? Monday's the exam. So make sure everybody remembers. But Wednesday, we're going to think about what can I interpret about directional derivatives and gradients in the context of level sets. Okay. Y'all have a good weekend. Good luck studying for the exam Monday. And see you Monday.